Hey everyone, I hope you're having a good week. For this week's discussion, I chose number 12 on page 330. Prove that the sum, where we have index value equal to 0 here to n, of negative 1/2 to the j power is equal to 2 to the n plus 1 plus negative 1 to the n all over 3 times 2 to the n. So since it was a sum, I rewrote it underneath so that it actually looks like a sum, which makes it easier for me to understand the problem and do my base case. If I do something wrong, please let me know. So negative 1/2 to the 0 power plus negative 1/2 to the first power, blah, 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 dot, 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 plus, should have put that there, negative 1/2 to the n is equal to 2 to the n plus 1 plus negative 1 to the n all over 3 times 2 to the n power. So I'm going to have a base case that I'm going to prove that this works for because we're doing induction. And let's do p of 1. Then we have the sum of, let's see, from our index of 0 to 1, okay, of negative 1/2 to the j power. So let's see, that's going to be, first of all, negative 1/2 to the 0 power, and then plus negative 1/2 to the first power, if I'm doing p of 1, should be equal to 2 to the 1 plus 1, which is 2, plus negative 1 to the first power, all over 3 times 2 to the first power. So negative 1/2 to the 0 power is just 1, plus, and negative 1/2 to the first power is negative 1/2. So this side ends up to be, the sum should end up to be just 1/2. So let's see if this happens on this side. 2 squared is 4, and then minus 1 all over 6 is also equal to 1/2. So we've proven my base case. So now we need to make an assumption, okay? So we want to assume P of k is true, where k is a non-negative, where k is a non-negative integer. So that means that negative 1/2, just to rewrite it to the 0 power, plus, and I'm just going to write out my sum here, negative 1/2 to the first, whoops, to the first power, plus negative 1/2 squared, plus, and again, plus negative 1/2 to the k power, there we go, is equal to 2 to the k plus 1 plus negative 1 to the k power. Oh, this is all from memory. I hope I write this down right. I'll check in just a second. All over 3 times 2 to the k power. So k plus 1, negative 1 to the k, all over. Okay, so I think that's right. So I'm going to assume that this is true. So what I actually need to prove is, okay, that this, and sorry, you guys, here, I'll pause it so you don't have to watch me, right? Okay, you guys, so I finished writing up that sum, but instead of ending at negative 1 to the k power, I added negative 1 to the k plus 1. So the very next one after k, the next part of that series after the k is k plus 1. So then it equals to my original that it would have been just stopping at k, right? Which I assume to be correct, plus one more negative 1/2 to the k plus 1 power, okay? So I know that should be equal to, instead of 2 to the k plus 1, it should be equal to 2 to the k plus 1 plus 1, or 2 to the k plus 2, plus negative 1 to the k plus 1 all over 3 times 2 to the k plus 1. So I know what I have written here, right? I need to be able to prove that that is the same as here. So I have rewritten it down here just so I have something to work with. Can I make this left-hand side equal to this right-hand side here? So first of all, I need to add these two fractions together. So the first thing I'm going to do is change negative 1/2 to the k plus 1 to negative 1 to the k plus 1 over 2 to the k. And then I did this, I just changed it to times 2 instead of 2 to the k plus 1 because I saw that I had a 2 to the k here and a 2 to the k here. So it made finding my common denominator a little bit easier. I know if I multiply this first fraction by 2 and this second fraction by 3, I'll have a common denominator. So I'll multiply this fraction by 2 over 2 and multiply this fraction by 3 over 3 gives me, 2 times 2 to the k plus 1 plus negative 1 to the k plus 3 times negative 1 to the k plus 1 all over my common denominator of 3 times 2 to the k plus 1. And then it's just some algebraic manipulating to get to making it equal to what I want, which is still over here. I'm halfway through this. I keep freaking out that somebody else is going to get number 12 posted before I do, and then I'll be late. So what did I do next? So if you multiply this out, you get 2 to the k plus 2, which is what I wanted, plus 2 to the negative 1 to the k power, plus, there you guys, plus 3 times negative 1 to the k plus 1. And kind of here, I knew I had so much that already was correct, and I had the 3 times 2 to the k plus 1. So I knew that I wanted this to stay. This is part of what I wanted, and I wanted this to stay. So I just needed to figure out, how do I make this equal to negative 1 to the k plus 1? So what I did was I factored out a negative 1 to the k power right here. So I took out negative 1 to the k, and I was left with 2 plus 3 to the negative 1, which is just another way to say negative 1, and negative 1 to the k power times negative 1 is negative 1 to the k plus 1. So here I should have k plus 2, 2 plus -1, 2k plus 1, all over, sorry for the wavy line, 3 times 2 to the k plus 1. Therefore, since I have shown that my base case works, and I have gone through the inductive process to show, sorry you guys, I guess I should have written this out, the process to show that it also works for k plus 1. Okay. I know that P of n works for all non-negative integers n. Yay! Oops, now I meant that as an explanation point and it looks like a factorial, so n. Please let me know if I did anything wrong, I made any mistakes, or you have any suggestions. And I hope you all have a great midterm. Bye, guys.